Okay, so yesterday we labeled the periodic table. And so we labeled numbers on the left side of it, all right? And the first block started with a 1, so it was 1 to 7. The second one was 2 to 7. The third one was 3 to 6. And the last one was 4 to 5, all right? So you'll always want to have a periodic table with these numbers on it to help you out. Now, eventually you won't need the numbers on there because you'll just kind of know what they all are. But while we're still learning it, feel free to use that periodic table to help you out. Now, across the top here, we have numbering also, and it goes along with whatever kind of suborbital they're called, the shapes. So we have S's, we have the P's, we have the D's, and then we have the F's, and they just go from 1 to whatever it is. So there's one type of S orbital, so that's why we only have 2 electrons here, because for each suborbital you can have 2 electrons. The P's, they have 3 different suborbitals, so 3 times 2 gives us 6. So there's 1, 2, and then 3 here for the P's. And those were the 3 shapes of the dumbbells. So we had 1, 2, and then 3. All right, so the P's have 3 different shapes. The D's have 5 different shapes, and that's why 5 times 2 gives us 10. And the F's have 7, which gives us 14, all right? So that was kind of what we've done so far. We've also kind of played the game of Battleship, where we've picked an element, and then we've kind of been able to figure out, all right, what number and then what letter number combination would correspond with it. So for bromine, it would be 4, and then P5. All right, so we have kind of a coefficient, the 4, we have the P, and then we have a superscript of the 5. And that's how we would identify that spot on the periodic table. All right, so far this is kind of what we've done with the periodic table and figuring out like where the electrons are. Now, we're going to go through and actually figure out what each of these numbers and letters really represent, and we're going to kind of come up with a roadmap showing where each of the electrons are for every element, which means we're going to have to locate, if we were doing bromine, 35 different electrons. So we'd have to kind of tell it where all of those 35 are. And that's kind of the goal of this, is to kind of give a roadmap for where all the electrons are. All right, so let's start off with some rules. First off, we have the off-ball principle. And so an electron occupies the lowest energy orbital that can receive it. And this is kind of like straightforward in that, if you think about it, if this was hydrogen, 1 proton, and then hydrogen has 1 electron, if you could imagine that these are all the energy levels around it, so like there's different energy levels, like the first one, the second one, and the third one, we normally would expect that that first electron is in the first energy level, just because it goes in order, right? Well, it actually is the lowest energy orbital. So if you can put an electron in the first energy level, the electron wants to be there because it requires less energy. So that 1 electron is going to be there. And because the first energy level can have 2 electrons, if we change this into helium, that second electron would also be in that first energy level. So you would get both of them in there. So you wouldn't get 1 in the first energy level and then 1 in the second energy level. All right? That's what the off-ball principle really is talking about as far as we're concerned this year. And then there's Hund's rule. So Hund's rule is orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. All electrons have the same spin. All right, we'll talk about what this all means shortly, but what that also kind of has to do with is once we get to the second energy level, so this is the first energy level, this is the second energy level, we know we can have electrons all around the second energy level, but they're not going to pair up the way that I actually drew it. What they're going to do is they're going to try to fill up ones that have the same energy first, and then they'll start doubling up once they're all filled. And there's a special thing that we'll go through with this as well, because it's not exactly as I'm showing it here, but that's the general idea, is that they would kind of fill up individually and then start doubling up, all right, as long as they have the same energy level. And we'll talk about the same amount of energy in a second, all right? So I just wanted to give these definitions before we get into actually doing some electron configuration. All right, so I put some rules here. Now these rules should help us to understand what I'm doing with drawing all of these arrows in a moment. So first up, a single-headed arrow is an electron. All right, so if we want to represent an electron, we would draw this kind of like, almost like a European number 1. All right, it's a single-headed arrow. So the first single-headed arrow you put is an up arrow, so it'll be pointing up, and that just represents the spin of an electron, because electrons can spin around clockwise or they can spin around counterclockwise. And we like to even them out because it just kind of makes sense, right? Nature likes to even things. So if you have one spinning clockwise, usually you'll have another spinning counterclockwise to balance it out. Doesn't always work out perfect, but that's kind of what we're going for. And you'll see the exceptions in a moment. There's one of these per box. If you have groups of boxes, each can have one arrow. So what they're talking about here is, if you're like filling up this where they're all at the same level, you would kind of fill them up one at a time. So if you needed to put 3, you would kind of space them out here. And that's what Hund's rule was talking about, all right? You would space it out. But they have to be exactly the same energy. So these 5 here, they are exactly the same energy. So you would just kind of fill them all up, and then you would put another electron in there. And the second one, remember, is down arrow because we want to even out the spin. All right, but that's getting ahead of ourselves. So let's erase that. Okay. All right, so there's one per box. If you have groups, we just did that, okay? If you need an additional electron, then you add a down arrow to each box. And that's kind of what I was just showing right on there, all right? So let's try to do just hydrogen, okay? And we need to identify a couple things also. So first of all, the 7 equals the energy level. Oops, somebody's at the door. Hang on. Okay, sorry about that. So the big numbers here are the energy levels, okay? So if we wanted to put one electron, and these are all the energy levels, right? So we have the first energy level down at the bottom, we have the second, third. Now you might notice that the second energy level has 2 of these letters, right? Well, that corresponds to that suborbital stuff we were talking about before, where you have the S's, the P's, the D's, and the F's. So all that stuff is also displayed here. And you'll notice that there's only one type of S. That's why there's only one box. The P's, there were 3 types of P's. Remember the different dumbbells? So that's why there's 3. The D's have 5, and the F's have 7. And we also talked about how the S's, they only have one shape there, but you can put 2 electrons in there. And then this has, 6 electrons, because 2 times 3 gives you 6. 5 is 10, and then this is 14. So this representation here shows you that the D, for example, has 1, 2, 3, 4, 5 spots, and each of those boxes can get 2 electrons. So it's a representation of how many electrons you can get in each of these suborbitals. But again, I'm over-explaining it. Once you see it in action, it makes it much more easy. So let's first start off with hydrogen, like I tried to a minute ago. So let's say we have the nucleus down here, all right? So here's our nucleus, and we're just going to have 1 proton. This is the first energy level. The first energy level only has an S. So we're going to show one electron by putting an up arrow in that box. So that's it for hydrogen, all right? It's just one up arrow because it has one electron, and it's in that 1s because of the rules. The rules being the off-ball principle, an electron occupies the lowest energy orbital that can receive it, so the lowest option we have is the first energy level, and there's only one, so we don't even need Hund's rule, but we'll get into that shortly. And so that would be hydrogen. Okay, any questions so far? I know we haven't really done much, but... Okay, so check this out. Keep going with me if you don't mind, and it'll make more sense, I promise, as we go through. So let's talk about helium. Helium has 2 electrons, and they're both in the first energy level. So we have one already here. The second one would be there. So that would show us helium. There's one up arrow and one down arrow. So it goes with the rules, all right? We put one in each box, but then we can't go to this 2 box because there's still an option for a spot in the 1 box, all right, in the first energy level. So you need to finish filling up the lowest energy levels and then you can move on to the next one, all right? So let's do beryllium. Beryllium's number 4. So now we're up to 4 protons. We have 2 here, and then we would have 3, and then 4. And if we drew beryllium, here's the nucleus. First energy level, 1, 2. Second energy level, 1, 2. So we have, this is representing the 1s. This is representing the 2s. So again, we're still following the rules of first energy level has 2. Second energy level can have up to 8. All right, but beryllium only needs 4, so we're done there. All right. Now let's do carbon. All right. Now with this, we kind of have to start over for each of these. But you can just keep going on yours because you'll see that it'll just keep adding up. So carbon is 6. So we would do 1, 2, first energy level filled. 3, 4, the 2 S's filled. And now we need 2 more. So we would put 1 here, and this is the first time we would use Hund's rule. The second one goes here. It's spread out because they're all electrons, right? They're all negatively charged. So if they can occupy the same low energy orbital but be spread out, they're going to do that. It's almost as if they were getting on a school bus and they don't want to be around other people because of COVID. So what would they do? They're going to sit in different spots. They're going to spread themselves out, right? And then COVID's probably not the greatest example because as it fills up, you are going to have to sit near other people. So maybe not the best. But that's kind of the idea. So if we keep going, if we go to something like oxygen, let's check out oxygen. Oxygen has 8, all right? So we start off at the beginning. We have 1, 2, 3, 4, 5, 6, 7, 8. So then you can start doubling up with that, all right? So then you would get 8 would be here, this down arrow. And if we go all the way to neon, it would be 9, 10. So now this represents the first energy level of 2, the second energy level, which is all of this, would be 8. So we have 1, 2, 3, 4, 5, 6, 7, 8, because this is all the second energy level. 1, 2, 3, 4, 6, 7, and then 8. All right, so that would be it filled up there. Any questions with what I just went over? Because that's that's pretty much all the rules with kind of going through this. But we are obviously going to do another example. I just want to stop so you have a second to ask. No? All right, cool. All right, I'm going to reset the board. You have another one, I think, next. Oh, I have another one too. All right, so what we're going to do is we're going to do what it says here. We're going to go through arsenic, and we're going to do it together, all right? So arsenic is number 33. So that means we're going to have to draw 33 arrows on this diagram. So we need to get up to 33. All right? And all you do is just kind of go in order. So, for example, we have 1 and 2 here, so that's 2. 3 and 4. This is the only part where it can get tricky, but we have 5, 6, 7, 8, 9, 10, which is where we were before, right? So we're at 10. Next thing we do is we go from 10 to 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That one's lower, so we have to go to that one first, right? Because as we move up, we're increasing energy. So we have to keep the energy low. Oh man, I forget what number I was at. I'm at 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. All right? So what we just did was we showed where all the electrons are for arsenic, okay, by filling this in. The next part of this is just writing it all down. So we start at the beginning, which is here, 1s. How many 1s's arrows do we have? We have 2, right? Because there's 2 arrows in there. And then we look at the next one. The next one's 2s, 2. The next one's 2p, 6, because there's 6 arrows. Then we go to 3s. There's only 2. Then we go to 3p, 6, because there's 6 in there. Then we go to 4s2, 3d10, 3d10, 4s2, 4p3. In a perfect world, we'd be able to write them all in a straight line and it would look nice. But I ran out of space here, so it doesn't look great. So what we've done is we've identified where all the electrons are located. So this is the first energy level. This is the second energy level. Both of them. They both have 2s. So second energy level. This is the third energy level, but this is where things get weird. The third energy level is everywhere there's a 3, which is now, this is our first experience where we see that you can have more than 8 electrons in an energy level. This one has 18, which is more than we've ever seen before. And then the fourth energy level only has 5, all right? So this is the third energy level, and then the fourth.